Hello, everyone. I just made it 6:10. There you go. So sorry, I'm running a few minutes late from my last meeting. So give me a few minutes to set up here, but nice to see some people. Um, if you have any questions while we're just waiting for me to get set up, just let me know. You can type in the chat, and I will record. I'll post the notes, all that good stuff. So just give me a few minutes to get set up here, okay? And then I will start very soon. Okay, everybody. So I think I'm ready. I got everything down here. So, um, well, let's start by how's everybody doing? How's everybody feeling about the midterm for 510? So we're here to talk about MTH 510, right? We're all on the same page. MTH 510 midterm tutorial for MTH 510. Um, yeah, how's everybody feeling right now? Feeling good. Okay. Kind of lost. Okay. Understandable. Decent. So, well, I chose a couple questions from a textbook, and of course, based off of what is typically covered in this midterm. So it's going to be very similar to like a sample midterm, but I just kind of pulled it from either random places or from the textbook or from things like this. So it's not exactly a sample midterm. I also won't be covering today anything MATLAB related. It's really just the numerical stuff. Well, obviously the whole course is numerical stuff, but the algorithms, the specific algorithms. Really good, decent mixed feelings. Someone's asking if it's recorded, so absolutely. So I'll comment on that later, right? But they the recording will be available. It's already recording actually from Zoom. I don't even remember clicking starting record, but maybe someone else did that who's here. I don't know. And so it's recording on Zoom, and then I'll also be recording myself and putting it on my YouTube channel. So you can take a look there. Okay, so let's get to it. So let me share my screen. I guess I can also show my face. Hello, but I don't want my. Oh wait, why is it not? Oh, I guess I can't show my face actually because OBS is open. So let me. There I am. Oh, I'm going to be tiny. Oh, tiny in the corner. You'll see me in a second. And yeah, so I'm going to be covering like the main things that are important in this course. And so the main things being, well, we'll see in a second what the main things are. But yeah, so probably close that. Okay, so in just a second, so I will start recording on my end as well. I will share my screen, and there's my screen, and now it's like an infinite kind of loop. And now, hopefully, no, I don't. Your screen share is paused. That's not what I want. That is not what I want. Okay, so I will stop sharing, and I will just share regular my whole screen. Okay, that should now be okay. You should see everything now, hopefully, right? So I'll keep the chat in the corner so I can see the chat, but everybody's welcome to unmute or you can raise your hand if you want. I probably won't see it though. I don't know how I'll see it. So yeah. So let me comment first. So I am recording on everything, right? So just make sure this I'm recording on. Yes. Okay, so everything's recording. So okay. So now let's get into some of the details. So what are the details? First of all, this is being recorded, right? Recording, right? So first of all, it's also going on my YouTube channel, which is just my name. Okay, and probably Muse will have something to do with it too. I don't know. Maybe Muse usually posts it on, it's like muse.ca/academics, I think, something like that. For the academic stuff, right? And that's where, but it's also posted on my YouTube channel, which is just my name. Okay, that's the first order of business. Now, well, what are we going to cover today together? So this is what I have kind of planned, right? So first, we're going to just talk about there's basically like 4 kind of parts to this, right, that are usually covered at the start, which is just, info, part 1 is kind of be like, info about errors. Okay, we won't spend that much time on info about errors unless we have time at the end. The second part is going to be like solving non-linear equations. I hope everybody sees my screen, right? If you don't, then tell me that. Next thing is going to be like LU factorization. The next thing we're going to talk about is going to be Gauss, iterative methods for solving systems of linear equations. And then the last thing we'll talk about is solving also iterative methods, right? So for solving nonlinear systems. Thank you, someone confirmed that you can see my screen. That's great. So we'll slowly talk about all these different things, mostly from textbook questions and from questions just online, whatever, right? So okay. So hopefully, I think it's going to be pretty much all from the textbook except the very first question. All right. So hopefully this sounds like a plan for everybody. The PDF will also be posted, right? So I'll mention that now, right? PDF also posted, will be in the description of video. Okay, so that will be posted. Okay, so if anybody has any question, so I already asked the general, how's everybody doing? So okay, so we got some good. How's everybody feeling for the exam? Decent. I got a little bit of that, right? Well, the thing about this course is it's fairly repetitive, right? Because you have just these algorithms that you kind of practice much time. There's a crux of the pre-midterm stuff or the midterm stuff. But then there's also the MATLAB stuff, right? The MATLAB stuff is also a difficult thing. And so I know you have labs with your TAs that you've been doing that. And I have some friends who are TAs for 510 this semester. Um, and yeah, so we're going to focus together here on kind of more the theory part, and then actually applying it not to MATLAB, but applying it to solving, typical kind of numerical analysis problems. Okay, I think that's enough talking. Let's get to it. Oh, we will take a break at, we kind of already took a break because I kind of was here a little bit late, but I was only a few minutes late, really, at the end of the day. So we'll still take a break. All right, so unless anybody, feel free at any point to raise your hand, unmute, shout at me, say this doesn't make sense, or you want me to explain better. You don't have to shout if you don't want to. You can also just politely just tell me what's wrong. Or if for some reason something glitches out and you can't hear me or something, just tell me. But also I have the chat open. So I have the chat in the corner. Is there like a big rectangle on the screen here around these corners? Is that what it's showing you? I think so, right? Yeah, okay. Well, and not much I can do. That's the chat right here, right? So anyways, I'll just avoid that little area and then we should be okay. Okay, so the first question is going to be this. Okay, so I'm going to have to kind of like handwrite the questions here. So question 1 is going to be determine the fourth root of 13 to 4 significant figures. Using bisection method. Determine the fourth root of 13 to 4 significant figures using the bisection method. Okay. Well, the bisection method, right, is telling us a way to get approximate solutions for nonlinear equations, right? So remember, we need a nonlinear equation, right? We don't even have an equation here. Well, if x is the fourth root of 13, that means x to the 4 is 13, which means x to the 4 minus 13 equals 0. Okay, and now for this, right, there's our nonlinear equation, right? That's kind of like our function f of x that we're trying to find the root for. And we have this important fact, and this fact comes up constantly when we're doing, theorem, constantly when we're doing bisection method, right? So if f is continuous, and f of a times f of b is less than 0, then we have some f of c, some root where c is between a and b. Okay, so you don't have to copy this. This is just what we're saying, right? Which is like if I have this fact that if I take the product of f of a, f of b, and that's negative, and it's negative means they have opposite signs, right? Then there's some c, right? There's some root in the middle. Maybe we call it r even, right? There's some r in the middle of a and b that must make it 0. And this is importantly if f is continuous. So we're going to use this a bunch of times, right? So we first need to find some interval where this happens, right? So if our function f of x is x to the 4 minus 13, right? Then we need to find some interval where this happens. There's ways to justify what's going on. I mean, if we just think about the fourth root of 13 for a second, I mean, also this might be given to you in a question, right? So we don't stress this part too much. They might just tell you on the midterm, just like, do bisection method starting with some interval, right? But like the fourth root, we can just think about it for a second. The fourth root of 13 is definitely definitely bigger than 0, okay? And above, well, you can do some bounds, but I mean, you can also just like approximate it with a calculator, or you can do we can do some logic, but I don't want to get too far into it. Let's just say, it's definitely less than, let's say 2 or 10 or whatever you want to say, right? But it's approximately like 1 point something. So we can start with this here like this. So I guess actually this is going to be kind of relevant. So I'm going to need a calculator a lot, right? And I don't want to just do a bunch of calculations off screen. So I think I'll just use like Desmos scientific calculator. I'll do that maybe on screen, because if I'm just doing a bunch of calculations off screen, that's not particularly interesting. So I'll try my best to do it here, right? And of course, this is not the point, but like the fourth root of 13 is like 1 point. That's what we're trying to find, right? We're trying to find this value. So you see it is less than 2. Anyways, you probably would be given a value. Okay. So that means that we're trying to hone in, right, on this value. There's our x-axis. There's the fourth root of 13, right? So uh, uh, if I plug in 0, right, then this is of course negative 13, which is going to be some negative number. So f of a is less than 0. And if I plug in 2, this is going to be some f of b greater than 0. And according to the theorem that I wrote up there, somewhere in here, there must be a root, as we can see there is, right? Our guess is just the middle, right? Our guess is just the middle always. Okay? So we can set up like a little table, and we can think about what this table, a lot of the time in this course, you like set up a table, but you should think about a little bit, what's the point of the table, right? So this is going to like kind of keep track of our iterations. And then on the next one, there's like a lot of things you could include, right? But what we really need to keep track of is the upper bound, right? So I'll say, the lower bound, the upper bound, and then the guess for the root, right? So you can say like x lower, xr, and x upper, right? And then you can always compute this kind of relative error, right? So it's relative error here. And we have this, well, we'll talk about, there's another column you can have for a second. But this is like the basic thing for bisection method. Oh, siren going by. I don't know if you can hear it, but anyways. So for our initial guess, right, for the 0th index, right, we have that this is just like from 0 to 2, and our guess is right in the middle is 1. And I can't compute relative error because I've only done one iteration of it. Okay. This may or may not be a good guess. Who knows, right? Okay, but then for to get to the next stage, right, we need to find, f of all these values to figure out where the function is changing. So you may want to also include here a whole separate set of columns that are f of all those values. And it's your choice how you organize it, but let's say I'll organize it like this. So it would be f of L, f of XL, f of XR, and f of X upper, right? Like the upper layer, upper level. And so, of course, like if we just compute it here, right? We already know this one's negative, and we know this one's positive, and we should just also compute what's happening here at f of 1 is what it would be, right? So f of 1 is going to be 1 to the 4 minus 13. 1 minus 13 is definitely still negative. And we see that here, right? We see this in this picture, right? So maybe I'll draw this picture a little bit more accurately, but you don't have to know the picture to solve the question. I'm just kind of drawing it. So you can see here as well, but no matter what, you can also just plug it in. You see that we get a negative value there for x, the middle one. So far we've started with, we chose some interval, some closed interval that definitely contains a root. And then we chose the middle one as our guess for the root. And now we have to try to, whittle this down a little bit more. You always choose the middle one. So now what's our next interval going to be? Can somebody tell me in the chat, what is my next best guess of a closed interval that contains the root? 1 to 2, right? You just choose the pair that has opposite signs. So there'll always be a pair that has opposite signs here. Visually, you can see here that it must be in this second quadrant, the second half, but you can see it here too, right? There was a change in signs between the middle, our guess for the root, and then our upper bound, right? That must mean that the root is somewhere in there, right? That's necessarily what that means. So our new lower bound is going to be 1, and our new upper bound is going, well, it's going to stay 2. And so our guess is 1.5. It's always going to be halfway in between. And now we just kind of repeat this process. So of course, the upper bound is going to stay positive because it's still 2. Now in the middle, right, we have to plug it in, like we have to actually plug it into our function, right? So we have to actually compute f of 1.5. And let's just, we just f of 1.5 is less than 1. Right? less than 0, I mean, negative. And like you could plug it in and find that. And then f of 1, we already found f of 1 right there, right? F of 1 is going to be negative. So once again, right, we have that it's f of 1.5, right, is negative here, right, positive. But the next thing we should figure out is our percent error, right, our relative error. And so relative error is always, and we should talk about this for a second here, right? The relative error is always computed by, new minus old over old, times 100%. And so this is so for us that means our guess for the root, right? That's like new what is the question, right? So new guess for the root versus our old guess for the root. So just to fit everything on the screen here. Oh no, that's not what I meant to do. Oops. No, come on, stay there. Okay. So our new relative error is going to be, so our new guess for the root is 1.5. Our guess for the root is always the middle. This is our guess for the root. The new guess for the root is 1.5. Minus 1 was the old guess from the previous row divided by the old guess, right? And so this is going to be 1.5 minus 1 is 1.5, 0.5. 0.5 over 1 is 0.5. So 0.5. So this is around 50%, right? Well, exactly 50%. So our relative error is about 50%. Okay. And the next question is, how many iterations do we have to do? So we did 2 iterations. Great. I mean, our guess is getting better. So now our guess is 1.5, but I mean, I need 4 significant figures of accuracy. I mean, do I have 4 significant figures? I mean, if I just wrote 1.500, is that 4 significant figures? Well, we need to know basically based off of this stopping criterion here. We need a stopping criterion based on this approximate error, right? Relative error. And so, yeah, absolutely. And so what we're going to do is we're going to use what's called like the Scarborough error stopping criterion. And it's basically like this, right? And this is going to be a fact. So I'll put kind of facts in orange here. Fact. If you want n sig figs, then the relative error, then keep going in all, and this accounts for all iterative methods, right? If you want n significant figures, then keep going until the relative error is less than, and it's this specific number, okay? It's less than 0.5 times 10 to the 2 minus n. Probably bad color choice there. Let me choose blue. I don't know. If you want n significant figures in your answer, then keep going until the relative error is less than that number, 0.5 times 10 to the 2 minus. So, okay, so I want 4 significant figures. Maybe I'll relax it to 3. Just to make our life a little easier. Why don't I relax it to 3 significant figures? And so to get 3 significant figures, right, we need the relative error to be less than 0.5 times 10 to the 2 minus 3, which is 0.5 times 10 to the negative 1, which is 0.5 times 0.1, which is like 0.05. If I'm doing it right? Yeah, I think that's right. And so that's what we need our, which is 5%. So we need our relative error to be less than 5%. Our relative error on this stage was 50%. Okay, that's not great, right? So we need to keep going a little bit more at least, right? So let's do another iteration. So our next iteration here. So the root is somewhere in here, right? The root is somewhere between these 2 numbers. So it's somewhere between 1.5 and 2. Of course, 2 is still positive. 1.5 we found to be negative, and the middle is 1.75, right? 1.7. Plugging in 1.75, so f of 1.75, this will also be negative. So that means that once again, our root is somewhere in the middle here, but we have to check the stopping condition, right? So to check the stopping condition, we take the new value 1.75 minus the old value 1.5 over the old value, which was 1.5. You take absolute value of that, which is going to be like 0.25 over 1.5, which is something. And again, this is maybe now when I start pulling out the calculator a bunch. So 0.25 over 1.5 is, about 17%, right? Is around 17% is all I really care about. So probably just one more iteration, right? One more iteration will be good. Well, we'll see how it goes, right? So then let's keep going. So the third iteration here, right? Is that 70? Did I do that right? 0.25 over 1.5? Yeah, that makes sense. Okay, seems kind of really low, but it's okay. And hopefully everybody's following so far. All right, right? Bisection method. Okay, so then now the new guess is 1.75 to 2 again, right? Because it keeps kind of being in this range here. And then so our guess there is going to be, well, now it's a little harder, right? So it's whatever the middle of that is, probably 1.8 825. Is that what it is? I think so, right? 1.82, because the middle of that is, so it's 12.5. So yeah, 1.825, I think is what it is. And then is the number meant to be the new value? Is it? Maybe. Present approximation. Oh yeah, you're right. Did I mess that up? Yeah, I did. You're right. Thank you for confirming that. There we go. So that makes sense. So this is going to be over 1.5, and this is going to be over 1.75. So my bad. Yeah, you're right. I just it's new minus old over new. And so we can recalculate that, right? So 1.5 minus 1, 0.5 is going to be 0.5 over 1.5 is actually just about 33%. And then for this next one, it's going to be 0.25 over 1.75, which is about 14%. Oh no, this is about 14%. So yeah, I mean, obviously it's possible to make these kind of numerical mistakes, right? So that's important, but it is important that you get the relative error right. So yeah, I confirmed here now. I just wrote it wrong. Present minus previous over present. New minus old over new. And then, whatever, we also need, what was it? 2 minus 1.75 over 2. Obviously is that plus 1.75 is going to be 1.875. Okay, so that's our new root value. And so now again, we just kind of go through this process. So we can take a look at, we can take a look at, so our, we need these bounds, right? We need the signs for these bounds. So we already know this one's negative. We already know this one's positive. Now we need f of 1.875, 75, right? So this will be, well, we can type it in now, right? So we need, f of x is, what was it? It was x to the 4 minus 13, right? And so we want f of 1.875 is some negative number, right? So still negative. Again, our root is somewhere in this middle bit. And again, we need to calculate this relative error. So it's going to be the new approximation 1.875 minus 1.75 over 1.875. And then we can compute that. So 1.875 minus 1.75 over 1.875 is about 7%, right? And so this last one will, certainly be our last iteration, right? So again, our you see that this is kind of our interval. So it's going to be from 1.875 to 2, and we just really need that number in the middle there. So this is going to be whatever, 2, the average of 2 and 1.875 is 1.93. Yeah, 9375. 375, and that'll be kind of our final guess here for this, because text keeps kind of changing. The chat keeps moving weird. I don't know why. But anyways, so that'll be kind of our guess there, right? And the most thing, we don't want to focus too much on the nitty, the nitty gritty is important because you have to be able to replicate it. But I can't really, that's just you got to try it, right? But the process is what really matters here, right? So we set up a table, and the table is not kind of like, it's important what's on the table, but you don't necessarily have to memorize what's on the table. It's just kind of what is needed to be there, right? So we need to have our upper and lower bounds. We need to have our guesses, and then we need to have these f of blah, blah, blah values here, right? We need to have these to figure out if it's positive or negative. And then we have this kind of relative percent error every time. And so, I wrote this theorem, I wrote this fact, but, we really need really the work, and I drew this picture, but even all that, really, it's all on the table where you just kind of keep combining all the numbers over and over again. All right, so that's bisection method, right? I don't want to, delay too much, but that's an important method. And so there's other ways you could have also solved this nonlinear equation. You also have like secant method, and you also have Newton's method, and those are open methods, right? They're not bracketing methods. So bracketing methods means you have to have a closed interval that contains the root. But open methods, you just start with a guess, and so that would be like Newton-Raphson, and that is just a different process. We'll do something similar to Newton-Raphson, but we'll do it for larger systems. Okay, so I'll leave that question, but of course, if anybody wants to stop me, please feel free to type in the chat or unmute or whatever you want to do. We can talk about that. Okay, so the next question that we can do, because what time is it? Yeah, okay, we got time still. So let's maybe do what can we do? Yeah, we can do this one. So let's do this question 2. I don't know if it'll bring us to the end, but we'll see. So question 2 will be this. And it's a Newton-Raphson question. So solve the following using Newton-Raphson. And it's a system y equals negative x squared plus x plus 0.75. Y plus 5xy equals x squared, let's say do 2 iterations or something like that. Or even just 1 iteration. We'll see how many we end up doing, right? And we want our initial guess, because whenever it's Newton-Raphson, they should give you initial guess. And if they don't give you initial guess, just choose 0. So the initial guess is x equals y equals 1.2. Okay, so this is a question from the text. Okay, so, well, we want to do this. So let's think about this now. Newton-Raphson, it's a system of nonlinear equations, right? So we can't apply like linear algebra directly here, right? It's a system of nonlinear equations. But what we can do is we can get some approximate solutions. So the first thing that we want to do is we want to first just like write everything equal to 0, because it's just in a better form like that. So I'll move everything to the left-hand side. So it's x squared minus x plus y plus 0.75 equals 0. And then over here, we get, I'll move this one the other way, but then flip it, x squared minus y minus 5xy equals 0. So that's kind of our system, right? This up here, right, is going to be like our f of xy. And this down here is going to be like our g of xy. And so Newton-Raphson, we got some formulas. Yeah, it is meant to be. I don't know what I'm doing. I don't know why I make silly mistakes like that. It is meant to be minus 0.75. Thank you. So, okay, now, right, we want to solve the system. So with that, we need some formulas for applying Newton-Raphson to this kind of larger system of nonlinear equations. And this would be something that likely would be provided for you on a formula sheet. I think you know what the formula sheet looks like for the exam now, so you can take a look at what's there. And I think the specific one, the one for two variables, are there. So let's find it here quickly, right? So it's it's open methods. I guess linear system is probably under linear systems. I guess iterative methods, nonlinear systems. Yeah, so the formula sheet is scary for this course, right? Someone commented that, and it is a lot. But I think an important part is going through the formula sheet, and maybe you should do this on your own and just kind of putting a bunch of labels, right? So I understand you can't bring your own formula sheet into the. I mean, I don't know. Maybe that was told to you, but I don't expect that to be true. But regardless, you should print it or do it on your iPad or whatever somehow, and just label what each part of the formula sheet is about. I think that's a good kind of clears things up by doing that. Okay, okay, so Newton-Raphson looks like this, right? So this is the two variable Newton-Raphson for two linear equations with two, well, yeah, nonlinear equations. This is the analogy for that, right? And so there's a lot going on here, right? But no matter what, we're starting with a system that looks like, it doesn't actually show you here, right? But so this is our second variable at time I plus 1. Well, why am I starting there? Let's start over here. This is our first variable at time I plus 1 is the first variable at time I minus this huge expression, which is f1 is like our top function at time I. And then the derivative of the second function with respect to the second variable at time I minus and this was the second function at time I times the derivative of the first one time I with respect to the second variable. And then a mess on the bottom, but actually the two bottoms are the same, right? The bottom of both of these equations are the same. So in other words, right, to kind of translate it into what we want to do in this question, right? So something similar to this is on your formula sheet, I'm sure. And so kind of like that's from the textbook. Translating this into words that match this question, we have f and g, and we have x and y. So we have like x at time I plus 1 is equal to x at time I minus f at time I. So that's like f of xi, right? And then we have the partial derivative of f of g with respect to y, right? Because x2 is y and f2 is g at xi minus g at xi. And then over here we have the derivative of f with respect to y at xi. Okay, and then the whole bottom of this big thing we'll just call triangle for now. Okay, so we'll deal with triangle in a second. And then the same thing holds basically for y. So this is like giving us an update rule, right? It's telling us how to update x. So now we want to know how to update y. So we take the original value of y, okay, and then we do something to it. So what do? Well, it's very similar, but we just kind of change it. So I'm just going to show what the changes are, right? So this is going to be a f here. x. Right? And I guess it shouldn't just be of xi, right? It's xi, yi. The variable is not just x, right? So maybe that's why get rid of all these, right? It's at time I. This is all at time I. I mean, it can't be at time I plus 1, right? Because we don't know the values at time I plus 1. So I'll just put a couple i's next to everything here just to clear that up. So, it's fi, this is at time I, this is at time I, and this is at time I. Maybe the I should go here, right? Okay, so then continuing on with that, right? So we're gonna have a similar thing here, right? So this is gonna be G at time I, and this is going to be F at time I. And then minus, so again, this is gonna be F at time I, and this is going to be G with respect to X at time I, and then same kind of triangle on the bottom. And then finally, that triangle, right? That triangle is that huge expression on the bottom of both fractions. So it's going to be, well, the partial derivative of f with respect to x times the partial derivative of g with respect to y minus the partial derivative of f with respect to x, well, y, I mean, times the partial derivative of g with respect to x. Triangle, all at time I. All at time I. So yeah, I mean, what a mouthful, right? There's just so much to look at, but this is an update rule, right? Like given some xi, you can find xi plus 1 because of this, because we know f and g, we know all their partial derivatives too, right? And so we can find all these things. So probably that would be a good place to start. We want to find now, right? So f of xy is equal to x squared minus x plus y, right? X squared minus x plus y, I think it was minus 0.75. So then we should find, the partial derivative of f with respect to x, and we should find the partial derivative of f with respect to y. We need both of those things, right? And then similarly for g, of xy being x squared minus y minus 5xy, we need to find all those things too, right? Partial derivative of g with respect to x, partial derivative of f with respect to the g with respect to y, and there we go. Okay, so does somebody in the chat want to try to tell me what are these partial derivatives? So what's the partial derivative of f with respect to x? Anybody? Yeah, I'm getting a couple 2x minus 1s. I agree with you. I got a 1, 2x minus 1. I agree. That sounds right, right? So we take the derivative of this expression here with respect to x. So we just look at the terms that have an x in it, right? This is a constant with respect to x. This is a constant with respect to x. So they just go away. They just derivative 0. Derivative of this is 2x. Derivative of this is negative 1 with respect to x, right? Okay, now the other one with respect to y, it's just 1, right? Everything without a y, constant. Everything with a y, take the derivative. The only thing here is y. So derivative of that is 1. Great, okay, now we're here. And so we need the derivative of this g with respect to x. So what would that be? Okay, so I got 2x minus 5y. I agree, right? So this is derivative, this is 2x. Derivative of this with respect to x is 0. Derivative of this with respect to x is just everything multiplying with the x, right? Negative 5y. And then finally the last one, yeah, someone already ahead of me. You guys had it locked and loaded, ready to hit enter, right? When I move on to the next one. And the derivative of g with respect to y is exactly negative 1 minus 5x. Yeah, -1 minus 5. Yes, or -5x. Okay, so there we go. So those are our expressions, right? And the only difference between this and what you could have on your midterm is that it could be different functions. And you just need to practice taking partial derivatives. But partial derivatives really are just regular derivatives. So probably you know at this point how to take derivatives pretty well, right? And if you don't, then that would be something good to review just in general, but also in terms of this, I mean, it's just most of the actual, like the only difference per se that you could have in your midterm questions is that these could be different functions, right? It could be something with sines or something with exponentials, all of which are not particularly hard to take the derivative of. So that ends up being that. Great. So our d, partial f, partial y ends up just being 1 always, right? So basically, like with that in mind, we can just kind of like take away this partial f, partial y. And then I think that's up here too, right? We can take away that partial f, partial y. It's equal to 1, equal to 1. And nothing else is quite that simple, right? So now we go ahead and we change, we basically copy all this over, right? And we can just do one iteration. Already 2 iterations is gonna be too much. So we basically now want to rewrite these rules as with the actual expressions in mind, right? So okay, so I'm gonna have to start erasing and then rewriting. So f at time xi, right? Remember what f was. F is x squared minus x plus y minus 0.6. I really need more space here, right? I need to clear all this. So the first thing was f at time I. So f at time I is going to be xi squared minus xi plus yi minus 0.75. So it's going to be xi squared, I already forgot, minus xi plus yi minus 0.75. Okay, well, see, so we're going to run out of room really fast, right? So maybe I won't write the whole expressions down. Yeah, maybe I won't write the whole expressions down because, I mean, it's just like, it's going to take a lot of time, right? So why don't we just, instead of writing the whole expressions down, why don't we just try to compute this, right? Why don't we try to do one iteration, right? So we have that x0 is x0 and y0. In the question I stated that we should just, the initial guess should be that they're 1.2, right? So we have 1.2 and 1.2. So let's just go through it, right? So if I want to find, I guess I will copy this down again, but just so that I don't have to scroll so much, right? So actually I'm going to bring this back, but just not because I'm going to change it really, just because I'm going to, I don't want to scroll. So there, and then these I can just erase, right? This I don't need there. I can just, okay. So best way to go about this, right, is to probably calculate, sort of time I, just to emphasize the I dependency here, right? It is dependent on I. Probably you want to compute this first, right? So partial fi, partial f, partial x at time I. Partial f, partial x is 2x minus 1. So this is 2xi minus 1. I guess I'll write this, right? 2xi minus 1 times g with respect to y, -1 minus 5x, 5xi, right? Minus 2g, not 2, sorry, delta partial gi. So g with respect to x. G with respect to x is 2x minus 5y. So this is going to be 2xi minus 5yi, right? So with that in mind, right, that's kind of our expression on the bottom there. Let's think about what, xi plus 1, which for us is 1, according to this formula right here, is going to be x0 minus, and then the whole big expression on the top that, I don't want to write, and then partial 0 here, right? So we can, I don't want to write it just because it's going to be huge to write, but we can actually compute it. So x0 is 1.2 minus, now we need f of xi. Should I just write it? It's going to be. I'm just going to write it. I'm just going to write it because it's hard to. Maybe we don't have to do it for y. So we have this, delta 0 here, right? At time 0. Then on the top, okay, what we're going to do is x. So it's going to be x0 squared minus x0 plus y0. We're going to write it really small. x0 squared minus x0 plus y0 minus 0.75. Right? Then we need that to multiply partial g, partial y, negative 1 minus 5x0, and then minus g at time I. G at time I is x squared minus y. It's right there, right? So I'm going to try to write it so that I can see it here. It's really tiny, but so we're subtracting this at time I. So it's going to be x0 squared minus y0 minus 5, and I'm going to just have to write, maybe that, minus 5x0, y0. That has to go in there. Okay, and that's our update rule, right? So now we just do that. x0 and y0 are both 1.5, 1.2. So here we have, you compute something here, right? So you have 1.2 squared minus 1.2 plus 1.2 minus 0.75, and so on, dot, dot, dot. And this is just something you do in a calculator now, right? You don't have to actually write all this. Someone asked, will you post the recording tonight or tomorrow morning? I'll post it tonight. I'll post it on my YouTube tonight. Okay, so now we actually do this. For these questions, x1 and y1 are different. Right. We don't know x1 and y1 yet, right? That's what we're computing. We're computing x1 right now, and we're going to compute y1 later. Like we haven't done that yet. Is that what you're asking? I don't know if that's what you're asking. For this particular one, x0 and y0, yeah, are the same, but that doesn't necessarily mean that they will stay the same. Yeah. Well, the formulas are different. Okay. Yes, the formulas are different for the two. Yes, for sure. The formulas are always different between x and y, right? Because there's two different expressions. So now it's just a matter of like punching all this in, right? So we need to have this number. So x0 is 1.2 minus, and then here we have 1.2 squared minus 1.2 plus 1.2 minus 0.75, negative 1 minus 5 times 1.2 minus, and then we have 1.2 squared. It's helpful that x and y are both 1.2 right now, but just for this round, 5 times 1.2 times 1.2, which is just squaring it. And then we need to have the determinant on the bottom well, yeah, it's the determinant, but it doesn't really matter. And so then we have a bunch of things, right? 2 times 1.2 minus 1. And then we have negative 1 minus 5 times 1.2 minus, just saying a lot of numbers now, right? This is definitely not the most interesting part of the tutorial. 5 times 1.2. Okay, and there we go. There's our second guess for, for x1. Boom. Right? So that is our next value of x1. Or of x, right? x1 is our next value of x. Okay, and then now you would, dot, 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 repeat for y. Repeat for y. Which we can maybe save ourselves the headache just to get through more. I mean, we can spend the next, the next 20 minutes if you want to doing for y. But it's really the same thing, but slightly different expression. I mean, the denominator is going to be the same. It's still going to be, it's here, right? It's still going to be this kind of delta 0, right? Because I is 0 in this, right? To get this to be y1. But the top is going to be different, some big expression, and it's going to be something, likely no reason for it to be the same as this value here. Okay, guys, so why don't we take, maybe a quick 5 minutes, 5 to 7 minutes, something like that, right? And just to refresh here a little bit, take a moment, and then we can continue on. I think the next thing I'll talk about is iterative methods, and then maybe some LU factorization, and we did kind of everything else. So, kind of the second half will be on a little bit more linear algebra-y, matrices and things like this, LU factorization. Probably start with an LU factorization, and then see what goes with that. Okay, so anyways, let's take a 5 or so minute break, and then I will be back. So 7:05, say by definitely by 7:12, we'll be back at it. Okay, so everybody get a glass of water. Be back. All right, guys, let's get back to it. Um, I think I'm recording again. Everything's fine. I never stopped recording on Zoom, and oh, that's not what I meant to do. Oops. Let me fix that. And I don't need that at all now. I'm recording here. Yes, I am. Everything's good. Okay, everybody can hopefully see slash hear me. Well, not see me, unfortunately, not today, but hear me. All right. Well, I think let's just get back into it. So, um, the next question that I want to do is an LU decomposition, which is just a particular helpful, an important part of numerical analysis a lot of the time is doing these kinds of decompositions because there's some numerical tricks we can do once it's in these special forms, right? Just in general, like not even just about matrices, just we can if we can put something in a special form, then maybe numerically we can kind of exploit something that's helpful there. And you can't always put in those forms, but when you can, then that's good. So that's an important part of numerical analysis. So this is going to be our question 3. And so, solve the following. Okay, so solve the following using LU decomposition. So we're going to get a system here. Okay, so give me 1 second to look at this. Should be okay. Let's just try it. Let's see what happens. 3x1 minus 2x2 plus x3 equals negative 10. 2x1 plus 6x2 minus 4x3 equals 44. And negative x1 minus 2x2 plus 5x3 equals negative 26. So I'm going to just make sure I copied all that right. Okay. So we need to do some kind of LU factorization, which means we need a matrix. So of course, the first step is to write this as the matrix product, right? So we have this like 3, negative 2, 1, 2, 6, negative 4, negative, I don't know, I wrote it so weird, negative 1, negative 2, 5 times this column vector, x1, x2, x3, and that's equal to negative 10, 44, and negative 26. Okay, so we want to solve this system using LU factorization, which means we want to take the LU, do the LU factorization of this guy, right? LU factorization of this. So, once we have that, then we're golden. But let's get there. So, so I'll start by getting our matrix. Right? And so we have 3, 2, I'm just going to rewrite it. 3, 2, negative 1, negative 2, 6, negative 2, 1, negative 4, 5. And I'm going to start doing row operations on this so that I can get it into kind of an upper triangular form. And I'm just going to keep track of what my row operations are that I did, right? And we'd like to do it without pivoting. So this is the thing that I was considering at the start. I think maybe we have to pivot, but I think we'd like to do it without pivoting. Well, let me look at something quickly. Just 1 second. Let me look at something here. I don't know if anybody knows if it's been mentioned to do it with pivoting or without pivoting, but I think we can just do it without pivoting. So it should be fine. So so what's happening? We need to do row operations. We need to get rid of these guys, right? Those three guys we need to get rid of. So first of all, we need to get rid of these two. So first of all, we need to get rid of that one, right? So row two becomes row two plus k times row one, right? We have to pick this in such a way, we have to pick k in such a way that this becomes a zero, right? So right now it's 2 plus k times 3, and we want that to become 0, right? So the natural choice is negative 2, negative 2 over 3, right? So if k is negative 2 over 3, then the 3's cancel and those cancel, and they're going to be 0. So we want negative 2/3 minus 2/3 are 1. And then I'll do that again. So row 3 becomes row 3. And now, again, I need to get rid of this negative 1 here now. So it's going to end, but it's negative. So I'm going to add, 1/3 of row 1. So 1/3 of row 1 is 1 plus, or plus actually, not minus, plus, right? And then negative 1 plus 1 is going to end up being 0. Okay, so of course that will end up with, but on purpose, it will end up with 3, 0, 0. And then we also have to kind of sort out what the rest of these things are doing. So now I got to use our kind of thinking hats here a little bit and remember how fraction hats maybe is a better word. So 6 minus 2/3 times negative 2 times negative 2. So it's going to be 6 plus 4 over 3. So it's going to be 18 over 3 plus 4 over 3 is 22 over 3. Right? And then this one here is going to be row 2. I mean, obviously use a calculator for this, right? Negative 4 minus 2/3. So what is that? Negative 12 over 3 minus 2 over 3. So negative 14 over 3. And then the third row is also going to be changing. So it's going to be negative 2 plus negative 2 minus 2/3. So negative 6 over 3 minus, so negative 8 over 3. And then finally 5 plus 1/3 is going to be 16 over 3. Right? Okay, so a little bit of a headache, but, and who knows, maybe I made a mistake. It doesn't really matter, right? Like just the process is what matters here. And then we will get it into one last form here. So the last thing we'll do is we need to get rid of that 8 over 3, right? So we need to do, row 3 becomes row 3 plus some k times row 2. Okay, so now let's think about it. So I want that to end up being 0. So it's going to be negative 8 over 3 plus k times 22 over 3. I want that to end up being 0, right? So that means k times 22 over 3 equals 8 over 3. That means k equals, it's going to be 8 over 22, which is 4 over 11. So that'll end up being, that'll be what we end up getting to cancel this out, right? So it's going to be plus 4 over 11. And so the whole point of all that is so that eventually here, right, we get that this is going to be a 0. And this is going to be something, right? What is this going to be? Whatever this is going to be 16 over 3 plus 4 over 11 times negative 14 over 3, right? So let's just use a calculator for that. So it's, I can do a little bit in my head, but why spend so much time? So I'll just clear that. 16 over 3 plus 4 over 11 times negative 14 over 3 is, well, it doesn't give it to me as a fraction. That's annoying. Well, should we just, I do wish it gave it to me as a fraction. Can I put it in Wolfram? Let's see. Because everything else is a fraction, right? So why? It's 40 over 11? Okay. Someone said it's 40 over 11. I will trust you. It's 40 over 11. Okay, great. So that's our upper triangular matrix. And so that means that our original matrix, right? Okay, great. Thank you. Thank you so much. So the original matrix, 3, negative 2, 1, 2, 6, negative 4, negative 1, negative 2, 5. So maybe the pivoting maybe would have helped, but it's okay. We can do without pivoting. is going to be, it's going to be LU, lower upper, right? Lower upper. So lower we don't have yet, but upper triangular we have, right? It's going to be 3, -2, 1, 0, 22 over 3, -14 over 3, 0, 0, 40 over 11, right? And then the lower triangular matrix, right, will be mostly zeros still, right? But we'll have these three entries, and it's going to be the kind of like inverted sign of what we have here, right? So it's going to be like 2/3. We had to use the number 2/3 to get rid of that spot. We had to use basically -1/3 to get rid of that spot, and we had to use -4 over 11 to get rid of that spot. I'm just kind of picking our numbers off of here. Right, so that, well, I guess I'll take it with everything. So flip the sign. That and that. And so we have completed the LU decomposition by doing. Okay. Is everybody okay with this? That's our LU decomposition. A little bit of fraction work had to be done, unfortunately. So if you can do an LU decomposition, this is helpful. We like triangular matrices, no matter what. Triangular matrices are really nice. And so either, upper or lower. And so they have a lot of good algebraic properties. Oh, is this supposed to be one? Oh yeah, my bad. It's supposed to be ones down the diagonal. My bad. It's ones down by diagonal. Yeah, there you go. Now the comments are coming in. Yeah, exactly. It's supposed to be ones down the diagonal. Ones down the diagonal. Okay, there we go. So ones down the diagonal. Everything else is zero in that lower triangular matrix. And then yeah, and our numbers come from that. There we go. Yes. Okay, well, great. Now we've done that. Now we want to do we want to solve this system, right? So we want to solve solve the following. So there's our kind of B vector, right? So I can just call this AX equals B, right? So if we have AX equals B, then, but we said A can be written as LU, right? So it's LUX equals B. So I'm trying to solve for X, right? That's like the thing I'm trying to do here. So to do that, one way I can do this is I can call this Y. So UX equals Y, equals Y, right? And so this is my, like I'm making this substitution. And so then this becomes LY equals B. So what I'm going to first do is solve for Y. And then I'm going to solve for X. It seems like it's a two-step thing instead of a one-step thing, but it actually makes things a little bit easier. So we have our lower triangular matrix times, I just introduced this variable Y, right? Ly equals B. And then using that solution for Y, I solve this system here. So this is of course our lower, and this is our upper triangular matrix. So for our first part, right, we have to solve Ly equals B. So L is ones along the diagonal. And then here we had a couple numbers, right? So 2/3, -1/3, -4 over 11 times, Y equals, B. B was, B? B was all the way back up here. -10, 44, -26. -10, 44, -26. And then we want to solve the system, but it was actually quite easy, right? Because like the first equation, the first row tells us that X, I think it was X1, X2, X3, yeah. So that X1 equals -10. That's the first, I just read off the first row. X1 equals -10. Then, the second row, so I'll just put double star, I guess. The second row tells us that 2/3 of X1, which is -10, plus X2 equals 44. So of course, that just means that X2 is 44 plus 2/3 times 10, so 20 over 3, which is like whatever, some number, which someone can maybe type into a calculator for me and tell me what it is. And then for the third part, right, the third row, 1, 2, yeah, it's definitely a better way of doing this. Thank you. 152 over 3. Thank you. So then for the last one, we have negative a third times x1, which is negative 10, minus 4 over 11 times x2, which is 152 over 3, plus x3, which we don't know, is equal to negative 26. And again, now this is pretty simple, that x3 is going to be negative 26 minus 10 over 3, plus, whatever 4 times 152 over 33 is. So maybe once again, if somebody could type that in for me, that'd be great. And then our solution then for y, right? Y, yeah, okay, wait. So maybe the x's were not actually, these are not actually the best way of doing it. These should be called y1, y2, y2, y3, y3, right? Because it's y vector. I just called this y, it's a y vector, right? The y vector is going to be like y1, y2, y3, just, giving it some names here. Okay, thank you. Somebody's giving me that this is negative 120 over 11. So that means that our y vector is negative 10, 152 over 3, negative 120 over 11. And so we found y. And so now going back up to this, right? First step was solve for y. Now we solve for x, right? For our x vector. Ux equals y, right? So we have our ux equals y. So what was our upper triangular matrix? Well, this was our upper triangular matrix. This was our upper triangular matrix. Then we have an x, right? X meaning like x1, x2, x3. And that's equal to y. Y, what's y? Y is what we calculated in this last step, right? Is negative 10, 152 over 3, negative 120 over 11. And once again, this is also very simple to solve for, right? So let me choose a color and let's write it. So the very bottom row, how about I number them this time? 1, 2, 3, right? So the very bottom row is just telling us that 140 over 11 x3 is negative 120 over 11. So, what does this mean? This means that x3 is negative 120 over 40, right? Which is negative 3. That's great. Then our second row is telling us that 22 over 3 x2 minus 14 over 3 x3, but x3 is negative 3, right? Is equal to 152 over 3. And so then x2 must be, well, it's 152 over 3. So 22 over 3, x2 is 152 over 3. And I'll probably write this as, minus 42 over 3, just to keep it all over 3, right? 14 times 3, hopefully, is 42. And then I moved it over, right? So it's negative. And so then all the 3's can go away. So x2 is just going to be 110 over 22. I guess, right? 110 over 22, which is 5, apparently. 5, okay, great. And then finally our last one is the last row is going to be tell us that 3 times x1 minus 2, 3 times x1, which we don't know, right? Minus 2 times x2, but x2 we know is 5, plus x3, which we know is negative 3, is equal to negative 10. So we get that x1 is equal to negative 10 plus 3 plus 10 all over 3. So x1 is equal to 1. And there we go. And so we get our solution that the x vector is equal to 1, 5, what was it? 1, 5, negative 3. Is it necessary to work in fractions after finding the upper and lower triangles? right? This is the question. Sometimes it is, but for the purpose of the midterm, I think it's fine to start rounding at some point. Let me see. Can I even say that? Ideally, they give it to you when it's like it's just going to be whole numbers. You know, everything's just going to stay whole numbers. In actual, like if you're asking an actual practical question, then there is sometimes problems. We do sometimes have problems where the moment you stop using fractions, there are certain types of matrices where it becomes an issue. And so those are called ill-conditioned matrices. And there's something called the condition number, which you have talked about in this course, the condition number of a matrix, right? So if it's ill-conditioned, it means there's something with the condition number. And I think if it's a very big condition number. That detail I'm forgetting the second, but I think if it's a very big condition number, then actually you have to stay in fractions. Otherwise, the rounding error is going to get too big. I don't know if you have, I don't know what you've covered in lecture. So someone's asking if there's like relaxation coefficients. So that's like, yeah, there's like a method for certain kinds of iterative methods where you have like a relaxation parameter, which kind of, well, it does a lot of things, but it's just kind of another parameter you can kind of tune in it to make it converge, faster or better. I don't know what you've covered in lecture, but I don't think so. I definitely don't think that's covered in I don't think that's going to be on the midterm. But like, I'm not a TA. Okay, prof said we should ignore relaxation. Okay, great. So then ignore relaxation. Okay, and now the very last thing that we want to work on. So we did a nice LU factorization question and solving question. The last question, which I think will bring us to the end here. Well, maybe not. I don't know. We'll see how it goes, right? But the next question, at least, is going to be like an iterative method for a linear system, right? An iterative method. So, let me just write it here, right? So use.
Why can't you start talking about Friday? Yeah. Okay. So I'll answer that in two parts. The first part is
Some people are.
Friday.
Someone's unmuted.
Any connector you or explorer TMU access
Fine.
starts at 6 p.m. So that would be.
There we go. That was pretty loud unmuting there. Okay. Anyway, well, let's get back to it. So, so question 4 is going to be use Gauss-Seidel method to solve, 10x1 plus 2x2 minus x3 equals 27, and negative 3x1 minus 6x2 plus 2x3 equals 61.5. Okay, and then x1 plus x2 plus 5x3 equals negative. That should be negative. Wow, why am I making silly mistakes? Negative 21.5. So let me just check I copied all that right. So it's 2x minus 1. Okay, that looks correct. So no matter what it tells you, if it tells you to use the Jacobi method or the Gauss-Seidel method, no matter what, you need to start rearranging these equations, right? So we arrange each equation for their respective variable, right? So like we take equation 1 and we rearrange it for x1. So equation 1 is going to be 27 minus 2x2 plus x3 over 10. We take the second equation, x2, we're going to rearrange this for x2, right? So it's going to be negative 61.5 plus 3x1 minus 2x3, 1, right? Minus 2x3 all over negative 6. And then we take the third equation and we solve it for x3. So we have negative 21.5, negative 21.5, like that. Okay, and we're solving for x3, right? So minus x1 minus x2 all over 5. No matter which iterative method you use, you got to do this first. And so then basically what we do, this is the difference between the two methods now, right? So I'm going to ignore that it even said use Gauss-Seidel. I'll just do kind of both at the same time here. So now, if you want to do it using, okay, so this, let me kind of organize myself here a little bit. Okay, so that's just the general thing. Now I'm going to copy it here, maybe make it just a little bit smaller. And this here too, right? Okay. So now, okay, this will be for the Jacobi. This will be for the Gauss-Seidel. Okay. The point is this: if we're at, we want to have like an iterative method here, right? So we want to kind of, we have an initial guess for x0, for x1, x2, x3. We have an initial guess. I guess I should have put that at the start here, right? My bad. There's probably an initial guess in the question that I didn't see. Oh no, there is an initial guess. So if there's no initial guess, then just pick 0. So initial guess will just be x1 equals x2 equals x3 equals 0. All equal to 0. Okay, and so now we're going to have a sequence of approximations. Excuse me, a sequence of approximations. So if I want to get the I plus 1th approximation for xi, right, then I start with my approximations. I have to use my approximations at time I, right? So I'm going to use the I approximations here. And for Jacobi, we just use all of them at time I, like this. We use all the ones from the previous step. We calculate everything from the previous step, and then we calculate everything from the new step. I plus 1, I plus 1. Okay, so to figure out x1, 1, I use x2, 0, x3, 0. I don't use x1, 0, but I use those other things. Okay, the difference here with Gauss-Seidel is this. It starts out the same. To figure out the I plus 1th term, I still need to use, I don't have anything else to work with. I just have to use the I plus the ith value, the previous value. But now when I'm here, right, x1, right, I actually have 2 options available to me. I can either use xi, or I can use xi plus 1. And I may as well use xi plus 1 because xi plus 1 is slightly more updated. It should be a better approximation because it's from our next step, right? So why don't we use that better approximation already? X3 we can't do that, right? Because we haven't actually calculated x3 I plus 1. These are the I plus 1 terms here. So x3 I plus 1 we don't know, but x1 I plus 1 we just calculated. Similarly here, x1 I plus 1 we know, so we can use it, and x2 I plus 1 we also know because we just calculated it, so we can use it. So the only difference between the Jacobi and the Gauss-Seidel methods is what I'm about to highlight in orange. It's just that if we have the updated value, we may as well use the updated value. And in general, it converges better when we do. So I feel like I have not drawn a lot of tables today. I only drew one right at the start, and now I guess I'll draw one here, right? So just take a second and understand this, right? So we started with our system, we rearranged it into this form, and then from here, we're going to set up like an iterative method here, and there's kind of 2 ways to do it. Okay, so let's do it. So now the the actual question said to do it with Gauss-Seidel, so we'll do it with that. It didn't really give a stopping condition. I mean, we can just say like go until, well, this is from the textbook. What did the textbook say? Go until 5% relative error. Okay. But we should kind of talk about this, right? So let's maybe talk about it. So about the relative error is what I'm saying. So we'll draw a table. At each iteration, so at iteration 0, let's start, right? We have some value for x1 at time I. We have a value for x2 at time I. We have a value for x3 at time I. And we have a relative error, right? For number 1. We have a relative error for number 2, and we have a relative error for number 3, and then we have a total relative error. Okay, so we have kind of 3 relative errors. Double lines sometimes help to distinguish sections here, right? A lot of this course is drawing tables. So okay, so for the 0th one, I just said everybody should just pick 0, and you can't fill in any of these for the first for the 0th row. Okay, so great, that's fine. For the first iteration, now we need to do all this, right? Well, if everything's 0, right, then xi plus 1 will be 27 over 10, right? Will be 2.7. x2 will not just be negative 61.5 over 6 because we're using the value we just calculated, right? So, I mean, I'm not going to write it out every single time, but this is going to be like negative 61.5 plus 3 times 2.7, not 3 times 0. 3 times 2.7 minus 2 times 0, this one's still 0, over negative 6. Right? Because we use that value from the current step, not even the previous step. It's basically from the current step, but we already calculated that, so we can just do that. Okay, so I mean I have to just plug that into something, right? So let's do that. So many windows. So what am I calculating? I'm calculating that, right? So let's see. So it's going to be negative 61.5 times, plus 3 times 2.7. That's it, over negative 6, so 8.9. And then for x3, right, for x3, we use negative 21.5 minus 2.7 minus 8.9 over 5. None of them are 0 now because we're using only the updated values. Right, that's for x3. So it's going to end up being, so what did I say it was? It was negative 21.5 minus 2.7 minus 8.9 over 5. So we have negative 6.62. Yes, thank you. Negative 6.62. Okay, and now we can compute these errors, right? We can compute these errors here. So it's new minus old over new. So it's going to be, the new guess for this one is 2.7 minus old over new, right? So it's going to look like this. So this is going to be about 100%, right? And then the same thing is going to happen for all of them, right? Because for all of them, it's 100%. And then for the actual overall one, you take the maximum of all these. Well, the maximum is, of course, 100%. They're all 100%. So the maximum is 100%. Okay, so, but that's very important, right? So like, I'll just, emphasize that here. So if I have, the approximate error is the maximum of the absolute values of all the other ones. Of the individual ones, let's say, right? The individual ones. Okay, so, well, we would just do one more iteration. So let's do one more and let's just see what happens when we do one more iteration here. So one more iteration, we take these values and we use them to find x2, 2, right? So I is 2. So this is gonna be a lot of me just saying numbers now, right? So be prepared. So let's see, maybe I'll Can you see the calculator when I pull up the calculator? You probably can't. Not that you're missing much. Oh, you can. Okay, good. Yeah, again, not that you're missing much, but that's good that you can see it. Okay, so then we need all these numbers now, right? So let's do it. So the first one is going to be 27 minus 2 times x2 from the previous round, which is 8.9, plus x3 from the previous round, which is negative 6.62, all over 10. Great. So that's our new x. Yeah, right? Okay, that's our new xi, x1 value. It's kind of a big jump, right? But I guess, I don't know what happened there. 0.258, I think it was. 0.258, yeah. Okay, so now our next value is going to be for x2, and this is going to be negative 61.5 plus 3 times, not the xi, x1 from the last round. I'm going to use x1 from this round because I have the value. And this is for Gauss-Seidel. Jacobi, you just used everything from the previous round. But this is Gauss-Seidel. So minus 2 times x3. x3, I have to use the previous round. You just always use the most updated one. So for x3, I have to use the most updated one is negative 6.62 all over negative 6. So that's 7.914. Let's say. Okay, and then the next one is going to be for x3. So we have that this is negative 21.5 minus x1. Again, I can use x1, x2 from this round. So it's going to be 0.258, so minus that, minus 7.9143 all over 5. Okay, and that's going to be our next guess there, negative 5.93. Negative 5.93. And then we can compute all these relative errors as well, right? So for all of them, right, we do the new value, 0.258 over, minus the old value, 2.7 over the new value, 0.258. So it's about 900%, right? On this one. And then for the other one, we, absolute value, right? You ignore the negative sign. And then this one, we take the new value, so 7.9143 minus the old value, 8.9 over 7.9143, the new value. So this one's about, 12%. And then this one is going to be the new value, negative 5.93 minus the old value, which is negative 6.62 over the new value, which is negative 5.93. And so this is, again, negative 12. So we have, well, I mean, the sign doesn't matter, right? So this is going to be like 900%, 947%, 12 and 12. This is 947%, 12%, 12%. So again, we just take the maximum. So 947%, of course, is the relative error. So there's some weird jump that happened there with that value. Who knows why, or something with the coefficients. We can do some tests. There's ways to kind of talk about this convergence, but there's that idea. Okay, so you would keep going until something, the error is less than 5% was what the question was. So presumably the next round, this 947% error is going to go way down because there's not much else to modify, right? It kind of is it's kind of converging into the result. And yeah, so that is that. All right. So, well, I mean, that's that question. So that's kind of what I wanted to get through. Let's see. Is there anything that I didn't get through from the very start? Info about errors that I meant like the how many significant digits kind of thing. Solving nonlinear equations, we did that. LU factorization, we did that. We did that, and we did that. So the only thing left, I can think of one more thing that might be helpful. We still have 8 minutes, so may as well talk about it. Is actually related to the first question. But before I move on, any questions about this, about these iterative linear algebra system solving methods? Right, so there's kind of our big. So I'll just pause for a second. How do you make sure a matrix converges? This is a good question, right? So first of all, I think you mean like like some sort of like iterative method on a matrix. So like, how do you know for sure that it's going to converge, right? And this is actually a very important problem. Like we do need to know this. And I don't think you really need to know for the midterm. It doesn't really matter, but we can just see if they comment on it in here, right? So they may comment on it in the book. So let's take a look at iterative methods on Gauss-Seidel, whatever, and then we can see convergence and diagonal dominance, right? So yeah, so there's some conditions on the convergence, right? So Gauss-Seidel methods can diverge because its ability to converge is much more predictable than for fixed point iterations. It can be shown that the following, so if the following condition holds, Gauss-Seidel will converge. So that means that if if I guess for all fix I, right, choose some I. So the diagonal entries are the absolute value of the diagonal entry is strictly greater than the sum of the entries in the same column, right? Because J, what is it? I, so I is fixed, row is fixed. So in the same row is fixed, right? Yeah. So fix them I. So the same row, the diagonal entries are the largest absolute value. So we call that diagonally dominant. Diagonally dominant matrices are very nicely numerically stable. And so, but we don't deal with that so much in this course, right? So we kind of just, we have that. Was that the case here with this? Yeah, this was the case, right? This was the case. So you see that like 10 is strictly bigger than 2 plus 1. 6 is strictly bigger than 3 plus 2. And 5 is strictly bigger than 1 plus 1. So the diagonal entries are the largest in the row. They're larger even than the sum of all the other coefficients. And so again, we call a matrix like that diagonally dominant. And you can do row operations to kind of fiddle with it to get it in that form, right? So it's important too. Okay, so that's a good question. Hopefully that kind of clears things up. So the only thing that's kind of left to talk about, I just want to mention about the bisection method. Okay, so for the bisection method, I know I'm kind of like jumping. I don't mean to jump so much over. Like back to the start, right? But for the bisection method, we actually know we have an actual upper bound on the actual error, right? So we have this like xn sequence, which is telling us our approximations for it. And let's say xr is the actual root that we're trying to find, right? So we have some function that's located at xr, and then we have this sequence xn, right, which is supposed to be approximating it, right? And we have a bound on what xr minus xn is, right? Like what the difference between these two are. And it's going to be less than, we don't know what it, we have a bound on it. That's why I said, but I wrote equals. We definitely don't know what it's equal to. Because if we know what it was equal to, then that means that we know the exact value. But it's definitely less than, and now we're going to put something here, right? So it's like 1/2 to the n, something. But let's just think about it for a second, right? If I have, an interval, let's start with an interval here. And I'm mentioning this because this is often covered all these midterms, right? If I have an interval from a to b, let's say from xa to x, well, whatever, just from a to b, right? Then and I know the root is somewhere in there, right? I know the root is somewhere in there. And my guess is always the middle, right? XR is always my guess in the middle. How wrong could I possibly be? Well, the absolute worst case would be that the root is just barely at one of the bounds. It can't be at the bound because then f of b would be 0 and we'd find our root. So it must be just slightly to the right of b, or just slightly, or to the left of b, or just slightly to the right of a. Okay? That's kind of our worst case scenario. Okay? So the the worst case scenario for right off the bat is, and how far is that? Well, that distance there is certainly at most, right? That distance is at most, or sorry, at most I guess I mean like this, right? At most, 1/2 b minus a. Right? And then when I do that again, right? Now my next interval is here, and my guess is in the middle, right? Again, how wrong could I possibly be by making this XR? That my root. Well, this distance. And what is that distance? Well, it's a half of my previous one, 1/2 b minus a, which is going to be 1/2 squared times b minus a. And then I do it again, right? So then I say, well, my interval is going to be, here now. And again, my guess is in the middle. How wrong can I possibly be? Well, it's going to be this distance, which is again half of that. So it's going to be 1/2 cubed times b minus a. So in general, right, after n iterations, the distance between the actual root and my guess, I guess I'm kind of mixing values here, so I'm going to call it like x star is my actual root and xr is my guess. Right? So x star is this is my actual root right there, x star, is less than 1/2 to the n times the size of my original interval. So if I start with a really big original interval, then of course cutting it in half a bunch of times is not going to help us that much. But if I started smaller, then, well, I mean, obviously cutting it in half a bunch of times will eventually get it to 0, close to 0, not to 0, but as close to a small interval as you want it to be around the root. But starting with a smaller interval for b minus a is going to be smaller. So that's our exact expression for an upper bound, not an exact expression for the difference, but an exact expression for the upper bound of the error. This is like our like true error. This is not like relative error. This is true error, right? True error. The actual just difference between the right answer and what we have. And well, we know we're at most that wrong, right? We couldn't be more wrong than that. That wouldn't be possible. All right, guys. And well, with that, if in 3 seconds we are done for today. So it's 8 o'clock now, so that will wrap it up. So that's probably my last discussion here. But I'll stick around for a few minutes if anybody has any last questions to talk about, or just general questions about the exam. But otherwise, wishing everybody good luck on the exam. Hopefully this was helpful. I will post the video and I'll post the notes as I described earlier. And otherwise, yeah, I'll stick around for a few more minutes if anybody has any questions. But yeah, thanks for joining, everybody. Good luck on the exam. Sometimes it does this. Why does it do that? Okay. Stop recording here.